Hello, my name is Cameron Sampson, and I'm going to present to you today the time series analysis of urban expansion in the metropolitan areas of Canada using the Landsat archive. Humans altered the natural carbon cycle in many different ways. The impacts of human activities have long-term impacts on carbon stocks and net emissions, as well as removals and transfers of carbon. The most significant human actions are forest management, cultivation of soils, deforestation, drainage, and urbanization. Specifically looking at urbanization, urban expansion has been taking place twice the rate of urban population growth. These changes can result in either a loss or a gain of carbon. A loss of carbon would be something like a forest to an urban settlement. A gain of carbon would be an agricultural field to a park. The lack of estimates from this land use change is recognized as a gap in Canada's National Inventory Report of Emissions. In order to fill this gap, we need to use a continuous data set that covers all of Canada. And using Earth's observation data makes this possible, something like Landsat data, which we have coverage from 1984 to present. Now, if we looked at all of Canada, it would be 1,285 scenes and petabytes of data, which we just can't store. Even if we're just looking at the metropolitan areas, which is 56 scenes, it would still be terabytes and terabytes of data. However, if we're using a data cube methodology and segments, it reduces size, and we can actually scale this up to a national scale and do the smaller cities as well. So this methodology involves defining where the areas are for urban places, and it's defined by Statistics Canada. And then once we have these defined boundaries, we create segments or the polygons for the area of interest. So we use a Sentinel-2 image from 2018 to 2019, so just the most recent one, and then we use an object-based imagery analysis to create segments out of this image. And then we classify the segments visually, focusing really on high accuracy rather than a fully classified image. And the classification is done on a segment level, and it's not on a per pixel basis. Once we have this image segmented, we acquire the Landsat 5 and Landsat 7 data to build the time series, and we use these two satellites because they have similar wavelengths. And then once we do that, we actually build a time series of pixel values for each segment for Landsat image. So what we do is we go and we take the average pixel value inside each segment for each Landsat image, and then store all that information into a Postgres SQL database, and then run CCD analysis on it. So what is CCD? It's the continuous change detection algorithm. It uses Earth's observation data, so those values in the pixel segments, to create time series models. These models are composed of harmonics that capture the annual cycles and seasonal components of the data. When a model breaks or experiences a land use change, it classifies the break period and begins a new time series model until another break occurs. And then these harmonics are saved into the database for each band. So a bit more information to make it clear. So we have three images here. We have September of 1990, September of 2000, and September of 2010. And these are 3 time periods, or 3 years per each image. So we can see here in the bottom left that it starts in 1989 and then ends in 1991, and just represents all the wavelengths and all the bands for that image. We can see the red dot here is an agricultural field, and then it turned into an urban area. But looking at the wavelength bands, it's kind of hard to determine that, but with the naked eye. But when we run CCD on the image, we get something like this. So we can clearly see these harmonics in the image, and we can see that it captures the seasonal components and the annual components, and it's just a very continuous harmonic across, representing that agriculture area. But then we can see in September 2009, we can see this break here, and that really is the change in land use. And then a few more examples of continuous harmonics. So we here have a airport with a grassland, which we currently classify as agriculture. And we can see this continuous harmonic all the way across where there is no land use change. The same thing is for this forest that's in an urban area. Here we can see it's just a continuous harmonic across the entire time series. But when we get a change, we have that forest again, but instead of a continuous, it breaks in 2000, and then all of a sudden it's classified as a commercial area. And most likely someone went through and cut down the forest to build a residential area, and if they cut it down, there was probably no trees and it was just bare dirt and construction. And so it classified it as that high reflectance, and we get this commercial area. And then in 2013, it probably began to green up and people planted lawns and stuff, and all of a sudden it's being recognized as that residential area. And once we have all this information, we can run that random forest classification on the coefficients and the training data to actually go through each segment and classify each segment into these different time series. And then once we have all this information, we can just put it all into a database. And this is just an example of our attribute table that we get. So we have here shape ID is 1, and so this is the polygon, and it's a forest, and then in 1990, and then when it changed in 2000 it was agriculture, and then when it changed in 2014 it was residential, and if there is no change we just don't report any change. And once we have all this information, we can put a graphic like this. This here is representing the changes across time. So we can see it started in 1990, and we can slowly see those agricultural segments being changed into commercial, and then being changed back into residential. And so I'll let it loop once more through. So you can see lots of agriculture here at the beginning, and then it slowly is beginning to change into commercial and then into residential. So once we have all the information, we will develop carbon stocks as well with the University of Waterloo. So we're currently stratifying across Canadian ecozones, and then when taking into account the different land cover types that are within the class. So, and we're using object-based image analysis again and high-resolution ortho images to create these classifications. And then we're going to find Canadian-specific above-ground carbon to do this. So we can just see here what I mean is the bottom image is clearly a residential area, but we have gone through and we've really classified where the coniferous trees, deciduous trees, the grass, the pavement, the pitch roof, the water is, and then we'll have above ground values for each of these specific classes. And then once we have all those, we have just a percentage of how much pitched roof or how much grass is in a residential area, and then we'll be able to find the above ground carbon for that specific one, and like I said, stratified across different ecozones. And currently our overall accuracy is 93.4% for this. And then specifically looking at that a bit more, we can see that like a low density residential area has 26% trees, but only 3.4% pavement, whereas a commercial area has obviously less trees at 16.98, but a lot more pavement at 30%. And then if it's like a protected or recreation area, it can have up to like 42% deciduous trees and only 1.8% pavement. And so it really gives us a good idea of these different breakdowns per each class. And this is just for the Waterloo area. So our carbon emission estimates, we're going to calculate the pre and post conversion carbon stock changes for land converted to settlement from 1990 to 2019. So this is just using that activity data I talked about from 1990 to 2019, and then we're going to have these carbon stocks based on the classes and ecozones. And once we have both of these, we can calculate the emissions from the carbon stock changes in each land cover type. And this really just goes and improves the completeness and consistency of estimates reported in Canada's Greenhouse Gas National Inventory Report, and specifically for the land converted to settlements that I explained at the beginning is a gap in our currently reported inventory report, and we do not have those values, and so this will give us those values. Thank you.